A spacecraft drifts silently through the inky black, its hull pierced by an invisible force. The cosmos presents us with a beautiful lie. Its stunning nebulas and glittering stars hide a reality of extreme and constant peril. For every hopeful explorer, space is the most hostile environment we have ever faced. This journey will unveil 25 hidden dangers that lurk between the stars, threats every space enthusiast and future astronaut must understand. You will gain a complete and sobering map of the true risks of the final frontier, from radiation that rewrites your DNA to the slow unraveling of the human mind in isolation. How did astronauts survive a sudden explosive decompression, and what silent killer follows every mission beyond Earth's protective shield? The adventure of exploration is magnified by its very lethality. What do you believe is the greatest unspoken threat to our dreams among the stars? Our journey into the void begins with a threat you cannot see, hear, or feel until it is far too late. Cosmic radiation is the silent, omnipresent hazard of space travel, a fundamental barrier between humanity and the stars. This is not the gentle background radiation we experience on Earth, safely cushioned by our atmosphere and magnetic field. Out there, it is a relentless storm of atomic shrapnel. Protons and the nuclei of heavy elements stripped of their electrons are accelerated to nearly the speed of light by distant supernovas and our own sun. They become microscopic bullets of immense energy, capable of piercing through the hull of a spacecraft or the layers of a spacesuit as if they were tissue paper. When these particles slam into the human body, they do not simply pass through. They collide with the molecules inside your cells, shattering DNA strands and creating a cascade of damaging secondary particles. The effects are both immediate and terrifyingly long-term. Astronauts on the Apollo missions, traveling beyond Earth's protective magnetosphere, reported seeing sudden, unexplained flashes of light even with their eyes closed. These were not hallucinations, they were cosmic rays striking their retinas, producing tiny bursts of Cherenkov radiation as they zipped through the vitreous fluid of the eye. It was a direct, personal signal that they were being bombarded. For a short trip to the moon, the risk was deemed acceptable, but for a journey to Mars lasting many months or even years, the math changes drastically. The cumulative dose would be immense, significantly raising the lifetime risk of developing fatal cancers, damaging the central nervous system, and potentially causing cataracts or heart disease. Acute radiation sickness from a powerful solar storm, a torrent of particles ejected by the sun, could be lethal within hours if astronauts were caught without adequate shelter. Imagine being millions of miles from home, and your greatest enemy is an invisible rain that alters the very blueprint of your existence. The challenge for engineers is monumental. Shielding against this type of radiation is not as simple as adding more metal. Thick lead or steel walls can actually make things worse, as high-energy particles collide with the shield and produce a dangerous spray of secondary radiation like a cosmic shotgun blast. Solutions being researched are ingenious, using materials like polyethylene, which is rich in hydrogen and better at absorbing particles, or even creating magnetic force fields to deflect the radiation away from the ship. Some concepts look to using water or waste stored around the crew cabin as a protective barrier. This invisible killer forces us to rethink the very architecture of our vessels, reminding us that the first danger of space is woven into the fabric of space itself. While we shield ourselves from the distant stars, our own sun holds a more immediate and volatile threat. Solar flares and coronal mass ejections represent the raw, explosive fury of our home star, capable of unleashing chaos across the solar system with little warning. A solar flare is a sudden, intense flash of radiation across the electromagnetic spectrum, from radio waves to powerful X-rays and gamma rays. It is like the sun screaming in light, a burst of energy that can reach Earth in just over 8 minutes, traveling at the speed of light itself. This initial blast is the first wave of the attack. It can instantly overwhelm satellite electronics, disrupt radio communications across entire hemispheres, and pose a severe radiation risk to astronauts on spacewalks or in lightly shielded craft. But the true danger often follows in its wake. The same magnetic explosion that creates a flare can also catapult a coronal mass ejection, a CME, into space. Imagine a billion-ton cloud of searing, magnetized plasma, a solar hurricane larger than our planet, being hurled outward at millions of miles per hour. This is not light, it is matter, and it takes a day or more to travel from the Sun to Earth. When this titanic cloud of charged particles finally arrives, it does not simply pass by. It slams into Earth's magnetic field, compressing it on the day side and stretching it on the night side into a long tail. This interaction can induce powerful electrical currents in the ground and in our technological networks. The historical benchmark is the Carrington event of 1859, a solar storm of such magnitude that it caused telegraph systems across North America and Europe to fail, with operators receiving shocks and papers catching fire from the induced currents. Auroras were seen as far south as the Caribbean. In our modern, utterly electrified world, a storm of that magnitude would be catastrophic. It would not just be a blackout. It would be a cascade of failures. Satellites, the backbone of global communications, navigation, and finance, could be fried or permanently disabled. Transformers on power grids, which are massive and difficult to replace, could be overloaded and destroyed, leading to prolonged continent-wide power outages that could last for months or even years. For a spacecraft and its crew caught between the Sun and a planet without a strong magnetic field like Mars, a direct hit from a major CME would be a life-threatening event. The radiation dose would be acute and potentially lethal, forcing astronauts into a makeshift storm shelter surrounded by their water and food supplies for protection. We monitor the Sun constantly for these eruptions, but our warning time is limited, and our ability to shield entire planetary infrastructures is practically non-existent. The Sun gives us life, but in a moment of cosmic temper, it could also take our modern civilization back a century. This reveals a profound vulnerability, our deep dependence on fragile technology in a universe that can, with a single solar tantrum, remind us of our true place. The human body is a masterpiece of evolution, perfectly adapted for one specific environment, Earth. Remove the constant pull of gravity, and this intricate system begins to unravel in unexpected and profound ways. Microgravity is not a gentle state of weightlessness. It is a physiological crisis for our biology. The first visible sign is fluid redistribution. On Earth, gravity pulls your bodily fluids downward. In space, that force vanishes and fluids drift upward toward your chest and head. Astronauts often develop a puffy face and skinny bird legs in their first days, a condition jokingly called moon face. But the consequences are far from humorous. This increased pressure inside the skull is believed to be a primary cause of spaceflight-associated neuro-ocular syndrome. Fluid presses on the back of the eyeball, flattening it and causing swelling of the optic nerve. For many astronauts, this results in permanent changes to their vision, a lingering reminder of their time off planet. Meanwhile, the skeleton, deprived of the mechanical stress of walking and lifting, receives a catastrophic signal. Your body, in its ruthless efficiency, decides that maintaining strong bones is a waste of precious resources. It begins to reabsorb calcium, excreting it through urine, leading to bone density loss at a rate of about 1 to 2% per month. On Earth, an elderly woman with osteoporosis might lose that much in an entire year. This isn't just weakening, it's a rapid, silent decay that raises the risk of debilitating fractures during a mission or upon return to gravity. The muscles follow the same grim logic. Without constant work to fight gravity, the muscles of the back, calves, and legs begin to atrophy, to waste away. The heart itself, a muscle that no longer has to pump blood against gravity, can weaken and shrink. To combat this slow-motion disintegration, astronauts on the International Space Station become exercise addicts. They strap themselves onto specialized treadmills and resistance machines for over 2 hours every single day, fighting to trick their bodies into thinking gravity still exists. They are literally working out to maintain the bare minimum of what we on Earth take for granted. Yet even with this extreme regimen, the return to Earth is a brutal shock. Astronauts describe feeling as if they are made of concrete, their own bodies feeling unbearably heavy. They must be carried from their capsules, and they face months of intense physical therapy to relearn how to walk, to stand, to simply hold up their own heads. The body's memory of Earth fades with alarming speed, revealing a sobering truth. We are not just visitors in space, we are prisoners of gravity, and our freedom from it comes at a terrible cost to the very vessel that carries us. But the dangers of space are not solely written in the stars or in our own biology. We have created a threat of our own, one that now encircles our planet in a swirling, high-speed shroud of destruction. Orbital debris, often called space junk, has transformed the region around Earth into a silent, hypervelocity minefield. Since the dawn of the space age, we have launched thousands of satellites, rockets, and probes. Each mission left behind a trail of discarded rocket stages, loose bolts, fragments from explosions, and even tools dropped by astronauts. There are millions of pieces of this debris now, from defunct satellites the size of a school bus down to tiny flakes of paint and solid fuel particles. The true peril lies in their speed. In low Earth orbit, objects travel at roughly 17,500 miles per hour. At that velocity, even a paint chip carries the kinetic punch of a bowling ball thrown as hard as a major league pitcher. A marble-sized sphere of metal possesses the destructive energy of a hand grenade. For the astronauts aboard the International Space Station, this is not a theoretical risk. The station's modules are shielded against particles smaller than about 1 centimeter, but anything larger could mean catastrophe. The crew regularly receives alerts and must sometimes perform urgent avoidance maneuvers, firing the station's thrusters to shift its orbit out of the path of a tracked piece of junk. Windows on the ISS are frequently pitted by tiny impacts, and every spacewalk is a calculated gamble against an unseen bullet. The nightmare scenario, known as Kessler syndrome, is a cascading chain reaction of collisions. Imagine one large, dead satellite colliding with another. That impact doesn't just destroy 2 objects, it creates thousands of new, smaller fragments, each a new projectile. Those fragments then spread through orbital highways, increasing the probability of hitting other satellites, creating even more debris in an exponentially growing cascade. One major collision could effectively render entire orbits unusable, trapping us on Earth behind a barrier of our own making. This cloud of shrapnel threatens not just human spaceflight, but the very infrastructure of modern life. Our global communications, weather forecasting, GPS navigation, and financial networks all rely on satellites flying through this ever-thickening swarm. Every new launch, every satellite deployment adds to the problem, and cleaning it up is a monumental engineering challenge. Concepts include harpoons, nets, magnetic tethers, and even lasers to nudge debris into decaying orbits where it will burn up in the atmosphere. But for now, the minefield only grows denser, a sobering legacy of our first steps into the cosmos that now threatens to lock the door behind us. The silent menace of orbital debris is a slow-moving crisis, but space holds a far more immediate and visceral horror. The vacuum itself is a predator waiting just outside the airlock. Explosive decompression, a staple of science fiction, is often wildly misrepresented. Your body would not instantly freeze, nor would your eyes pop out. The reality is more insidious and just as lethal. In the near-perfect vacuum of space, the pressure is so low that the boiling point of liquids plummets. This triggers a condition called ebullition. The saliva on your tongue, the moisture in your eyes, and the fluids in your soft tissues would begin to vaporize, not from heat, but from the absence of pressure. Your body would swell, though your skin's elasticity would contain it, preventing a dramatic explosion. Simultaneously, the real clock starts ticking. With no air to breathe, hypoxia sets in within 10 to 15 seconds. Your brain, starved of oxygen, shuts down non-essential functions and you lose consciousness. You have perhaps 90 seconds of potential survival if brought back to pressure, but irreversible brain damage begins after just 1 minute. If you were holding your breath in that moment of decompression, the consequences would be even more catastrophic. The air in your lungs would expand violently, rupturing lung tissue and forcing air bubbles directly into your bloodstream, a fatal form of decompression sickness known as an arterial gas embolism. This is the same bends that deep sea divers fear, but in reverse, as dissolved nitrogen in your blood forms painful and dangerous bubbles throughout your body. The peril of pressure was demonstrated terrifyingly during humanity's first spacewalk. In 1965, Soviet cosmonaut Alexei Leonov ventured outside his Voskhod spacecraft. His historic extravehicular activity was nearly his last. In the vacuum, his spacesuit ballooned, stiffening so much that he could not bend his limbs to re-enter the airlock. His body temperature soared, and he faced the very real prospect of being locked out, doomed to asphyxiate when his oxygen ran out. With calm desperation, Leonov made a life-or-death decision. He manually bled precious oxygen from his suit to reduce the internal pressure, risking the bends to regain enough flexibility to squeeze headfirst back into the capsule. He survived, but the incident remains a stark lesson in how poorly we understood the physical confrontation with nothingness. Modern spacesuits are engineered to prevent such ballooning, and rigorous pre-breathe protocols using pure oxygen purge nitrogen from astronauts' bodies to ward off the bends before a spacewalk. Yet the vacuum's threat is never fully neutralized, only managed. It is a constant, silent presence, a fundamental hostility that reminds every explorer that the line between life and death is as thin as a spacesuit's membrane. One small tear, one faulty seal, and the universe rushes in with a cold, airless embrace. While the vacuum threatens to pull you apart, it also creates a thermal nightmare of impossible extremes. Space is not simply cold, it is a place where fire and ice exist side by side, separated only by a line of shadow. In the airless void, there is no atmosphere to gently distribute heat, no breeze to carry warmth away or provide cooling. This means an object in direct sunlight, with nothing to shield it, can bake at temperatures exceeding 250 degrees Fahrenheit. Yet, just a few feet away in shadow, that same object can plunge to nearly 300 degrees below zero. This staggering 600-degree swing is not a gradual change. It is an instantaneous, brutal transition at the terminator line, the boundary between light and dark. For a spacecraft or an astronaut on a spacewalk, this presents a relentless engineering battle. Imagine one side of your ship glowing cherry red from solar fury, while the other side is frozen solid in the deep chill of shadow. If left unchecked, these stresses would warp metal, crack critical seals, and cause electronics to either fry into silence or become so brittle they shatter. To survive, every vehicle that leaves Earth must become a master of thermal balance. They are wrapped in reflective, gold-colored multilayer insulation, a high-tech blanket that looks like crinkled foil. This material reflects the sun's intense radiation while trapping the spacecraft's own internal heat. To dump excess warmth generated by onboard computers and human bodies, spacecraft deploy large, delicate radiator panels. These panels, often with fluid circulating inside, are designed to radiate infrared heat directly into the cold of space, acting as the vehicle's air conditioning system. The design is a constant compromise, a dance between absorbing just enough energy to stay warm and rejecting the rest to avoid overheating. The peril of getting this balance wrong is starkly illustrated by the surface of the moon. Lunar dust, or regolith, experiences these wild temperature swings every 2-week-long day and night. This constant expansion and contraction makes the soil incredibly abrasive and challenging for machinery. For an astronaut spacesuit, the challenge is even more personal. The suit must protect its occupant from both the unfiltered blaze of the sun and the absolute cold of shadow, all while allowing them to move and work. A tear in that outer layer during a spacewalk could mean a localized spot on the suit heating or cooling catastrophically in minutes, transferring that lethal extreme directly to the human inside. This silent war between fire and ice is fought in every orbit on every mission, a reminder that in the emptiness of space, finding a comfortable middle ground is an act of technological defiance. The physical extremes of space are matched only by the profound psychological pressure of the journey itself. Locked inside a fragile metal can for months or years, millions of miles from home, the human mind faces a unique and grinding form of torture. This is not the dramatic panic of a crisis, but a slow, creeping erosion of sanity. Astronauts experience a brutal cocktail of stressors. There is the claustrophobic confinement, living and working in a volume no larger than a small apartment, with zero privacy and the same handful of faces every single day. Every sound, every habit, every minor irritation becomes magnified. Crew compatibility is not a nice to have, it is a matter of survival. A single difficult personality, a simmering conflict left unresolved, can poison the entire mission environment because there is no door to slam, no walk around the block to cool off. You are trapped with your crewmates and with yourself. Then there is the overwhelming sense of distance. On the International Space Station, astronauts can still look out the window and see the comforting swirl of Earth, a beautiful reminder of home just below. But on a voyage to Mars, a point comes where Earth shrinks to a mere pale blue dot and then vanishes from view entirely. This Earth out-of-view phenomenon is a profound psychological milestone. All of human history, everyone you have ever known or loved, every forest and ocean, is now hidden, reduced to a memory and a data stream. The sense of isolation becomes absolute. You are not just away from home, you are fundamentally disconnected from it. Sensory deprivation adds another layer. The environment is one of constant, droning machine noise, recycled air that always smells the same, and food that loses its texture and taste. The monotony of the routine, the sameness of each day, can lead to a state of lethargy and depression. Studies from Antarctic research stations, where winter-over crews are isolated for months in the dark, show clear patterns of mood decline, sleep disruption, and sometimes even cognitive hiccups as the brain struggles with the lack of external stimulation. Analog missions on Earth, like the HISEAS habitat in Hawaii, where crews live in a Mars-like dome for months, reveal how small irritations can grow into major disputes and how motivation can wane without careful management. So how do we combat this invisible decay? The first line of defense is crew selection, finding individuals not just with the right skills, but with the right temperament, resilience, and emotional intelligence. Once in space, constant, reliable communication with loved ones is a lifeline, a tether to normalcy. Mission planners now prioritize psychological support, using virtual reality to give astronauts a mental escape to a forest or a beach, and scheduling novel activities to break the monotony. The mind is as vulnerable as the body in the void, and safeguarding it requires us to engineer not just better ships, but a better understanding of our own fragile humanity in the ultimate locked room. That psychological isolation is grounded in a physical world of strange and hostile landscapes, where even the very ground beneath your feet becomes an adversary. Lunar and Martian dust, known as regolith, is far more than simple dirt. It is an alien substance with properties that make it a persistent, sneaky, and potentially toxic threat to both machines and human health. The Apollo astronauts discovered this the hard way. After their moonwalks, they would return to the lunar module tracking in fine, gray powder that got into everything. It clogged the joints of their spacesuits, making them difficult to move. It scratched their helmet visors, and its abrasive grit threatened to damage critical seals on their life support systems. The dust had a peculiar, gunpowder-like smell that lingered in the cabin. But what makes this dust so problematic? On the airless moon, solar radiation and constant micrometeorite bombardment have pulverized the surface rock over billions of years. This process creates dust particles that are not smooth and round like grains of sand on a beach. Instead, they are jagged, glass-like shards because there is no wind or water to erode their sharp edges. To make matters worse, the dust becomes electrostatically charged by the sun's unfiltered ultraviolet light, causing it to levitate and cling stubbornly to any surface, like a malicious glitter that is impossible to brush off. If inhaled, these microscopic glass shards could embed themselves deep in lung tissue, causing inflammation and scarring in a condition similar to silicosis, a debilitating lung disease found in miners and stonecutters on Earth. For future lunar bases, this dust is a first-order engineering problem. An airlock that is not perfectly designed could let this abrasive contaminant into living quarters, where it would slowly destroy sensitive electronics and become a constant respiratory hazard. Martian dust presents a different but equally sinister set of challenges. The red planet has a thin atmosphere and wind, which gives its dust a finer, smoother texture, more like talcum powder. It can create planet-wide dust storms that blot out the sun for months, but the greater danger may be chemical. Data from landers and rovers suggest Martian soil likely contains high concentrations of perchlorates. These are chlorine-based compounds that are highly toxic to humans. On Earth, perchlorates are sometimes found in contaminated groundwater and are known to interfere with thyroid function, which regulates metabolism. If Martian dust containing perchlorates is tracked into a habitat, it could contaminate the air and any water recycled from the humidity inside. If it gets onto spacesuits and is then inhaled, or if it contaminates crops grown in local soil, it could pose a slow, cumulative poisoning risk to crews. The solution will require a war on dust at every level. Future missions envision spacesuits that never enter the living quarters, remaining attached to the outside of habitats in special ports. Advanced airlock systems using magnetic fields or forced air jets might be needed to scour dust from suits and equipment before entry. Cleaning robots and specialized surfaces that repel dust may become essential technology. The dream of walking on another world comes with a gritty, pervasive reality. The ground we wish to explore is not welcoming. It is a clinging, invasive, and potentially poisonous reminder that in space, even the soil is out to get you. That clinging, toxic dust is a tangible obstacle, but the void also attacks our most fundamental connection, the lifeline of communication itself. As we venture deeper into the solar system, we do not just face distance, we face a profound and deepening silence. The speed of light, the universe's ultimate speed limit, becomes our greatest constraint. Radio signals, our only way to talk across the void, travel at that speed, but over interplanetary distances, even that is not fast enough. A command sent from mission control on Earth takes over 3 minutes just to reach a spacecraft orbiting Mars. A response takes another 3 minutes to come back. For a rover on the Martian surface, that round-trip delay stretches to an average of 20 minutes. Imagine a surgeon trying to operate with a 20-minute delay between seeing a problem and moving their hand. That is the reality of remote control from Earth. Real-time guidance is impossible. An astronaut on Mars facing a sudden equipment failure or a medical emergency cannot call Houston for help. They would have to describe the problem, then wait 40 minutes for a response. In a crisis, that is an eternity. This forces a monumental shift in operations. Future deep space crews must be the most highly trained, resourceful, and autonomous explorers in history, carrying the collective knowledge of mission control within themselves. They become their own commanders, engineers, and doctors because the comforting voice from home is only an echo from the distant past, but delay is only part of the threat. Communication can be severed entirely by cosmic geometry. During a solar conjunction, when Mars or another planet moves directly behind the Sun from Earth's perspective, our star's furious corona of ionized gas interferes with radio signals. For about 2 weeks, reliable communication becomes impossible. The spacecraft is on its own, pre-programmed with a set of quiet, safe activities to ride out the blackout. It is a scheduled period of radio silence, a reminder that the Sun still holds dominion over our conversations. Our ability to even attempt these conversations rests on a fragile, Earth-bound web of giant radio antennas known as the Deep Space Network. This trio of complexes in California, Spain, and Australia is the switchboard for the entire solar system, listening to the whispers of every distant probe. It is a single point of failure, a major natural disaster, severe terrestrial interference, or even a coordinated cyber attack could cripple our ears to the cosmos, leaving billion-dollar missions deaf, dumb, and drifting. We are building an interplanetary internet on a shoestring of light, stretched so thin that a whisper gets lost, and a conversation becomes a series of monologues sent into the dark. The silence of space is broken in an instant by a silent hypervelocity strike. While we worry about the junk we created, nature has its own arsenal of tiny, relentless projectiles. Micrometeoroids are natural particles, often mere grains of dust or sand, but they travel at staggering speeds, up to 160,000 miles per hour. That is nearly 10 times faster than a bullet from a high-powered rifle. At that velocity, mass becomes almost irrelevant. A speck of paint 1 millimeter across carries the kinetic energy of a 1-pound weight dropped from a 10-story building. For an astronaut on a spacewalk, a direct hit from a particle the size of a grain of salt could puncture their spacesuit, leading to a rapid, fatal decompression. For a spacecraft, a strike on a critical component like a fuel line, a coolant pipe, or a window could spell mission failure. The International Space Station bears the scars of this constant sandblasting. Its windows, particularly the famous Cupola observation module with its panoramic view of Earth, are marred by small, circular chips where micrometeoroids have vaporized upon impact, leaving a permanent pit in the thick fused silica glass. Each one is a reminder of a near miss, a tiny bullet that was stopped just in time. So how do you armor a vessel against an enemy you cannot see, tracking at impossible speeds? The answer is clever physics, not just thicker walls. Engineers use a design called a Whipple shield, named for its inventor. Imagine it as a spaced armor system. The outermost layer is a thin bumper shield, often made of a metal like aluminum. When a high-speed particle hits this bumper, it does not simply pierce through. It vaporizes instantly, transforming into a cloud of gas and molten debris. This expanding cloud then hits the main hull of the spacecraft, but its energy is now spread over a much larger area. The main wall can easily absorb this dissipated force, where a direct hit would have torn right through. Many spacecraft use multiple layers of these bumpers and high-tech fabrics like Kevlar or Nextel to further break up the debris cloud. It is a brilliant defense, turning a catastrophic pinpoint puncture into a manageable splash. Yet this threat is utterly random and constant. Spacecraft and stations are peppered with these tiny impacts every day. We rely on statistics and shielding, knowing that while a fatal hit is improbable, it is never impossible. Every mission is a calculated roll of the dice against a cosmic hailstorm of stone and iron, where even a speck of ancient stardust can become a weapon of immense destructive power. Our planet's greatest shield against cosmic radiation also creates one of its most treacherous traps. Encircling Earth like a pair of colossal, radioactive donuts are the Van Allen radiation belts, zones of such intense particle fury that they nearly halted humanity's journey to the Moon. These belts are a direct product of Earth's magnetic field, that invisible force that gently guides our compass needles. This magnetosphere acts as a cosmic fishing net, capturing the endless stream of charged particles blasted out by the Sun. Instead of letting them rain down on the surface, the magnetic field lines snag these protons and electrons, funneling them into two vast concentric rings around our planet's equator. The inner belt, starting about 400 miles up, is packed with high-energy protons. The outer belt, beginning around 8,000 miles out, is dominated by energetic electrons. Within these zones, particles spiral along the magnetic field lines, bouncing back and forth between the Earth's poles in a frenetic trap dance. The radiation levels here are not merely high, they are lethal for unprotected humans and can cripple unshielded electronics in short order. This presented the first great barrier for the Apollo missions. To reach the Moon, the spacecraft had to pass directly through these belts. There was a very real fear among mission planners that astronauts would receive a fatal dose before they even left Earth's neighborhood. The solution was a combination of speed and geometry. The command module's trajectory was carefully calculated to punch through the thinnest parts of the belts, and it did so at maximum velocity, limiting transit time to just a few hours. The spacecraft's aluminum hull provided some shielding, and the crew's exposure, while significant, was deemed an acceptable risk for the short journey. But the danger did not end with Apollo. Today, the Van Allen belts are a constant operational hazard for our satellite fleet. Global Positioning System satellites, for instance, orbit in a region called medium Earth orbit, which places them squarely within the heart of the outer radiation belt. Their electronics must be specially hardened or rad-hardened to withstand the constant bombardment that can cause memory bits to flip, software to glitch, or components to slowly degrade. The belts are not static. They are a living, breathing entity that swells and convulses with the Sun's mood. During powerful solar storms, the influx of new particles can supercharge the belts, creating waves of what scientists call killer electrons. These are particles accelerated to near relativistic speeds, possessing enough energy to punch through standard satellite shielding and induce damaging electric charges deep within a spacecraft circuitry. A single storm can suddenly pop satellites like electronic balloons, leaving behind only expensive, silent debris. We monitor these belts constantly, watching for their expansion and contraction, because our modern world of navigation, communication, and timing depends on machines that must daily run a gauntlet of trapped atomic fire, a permanent storm of our own making that hangs in the sky above us. Even the mighty Van Allen belts cannot stop the most energetic particles in the universe. Galactic cosmic rays are the unstoppable background radiation of deep space, a drizzle of atomic nuclei arriving from distant cataclysms far beyond our solar system. While solar radiation is a storm from our local star, galactic cosmic rays are a permanent rain from the rest of the galaxy. These are not mere protons from the Sun. They are the nuclei of heavy elements like iron and carbon, atoms stripped completely bare of their electrons and then accelerated to almost the speed of light by the shockwaves of ancient supernova explosions. Their energy is staggering, millions of times greater than anything produced in our most powerful particle colliders on Earth. This immense power is what makes them so insidious and so difficult to stop. Their flux, or the rate at which they arrive, is relatively constant, a never-ending sleet of high-energy bullets. But unlike solar particles, which can be partially predicted and shielded against with mass, galactic cosmic rays present a far tougher puzzle. When one of these heavy, ultra-fast nuclei slams into the aluminum hull of a spacecraft, it doesn't just stop. It shatters in a violent spray of secondary particles. Imagine it like this: a cosmic cannonball hits your ship's wall and explodes, sending a shower of nuclear shrapnel, neutrons, and other fragments flying into the crew cabin. This secondary radiation can be more damaging than the original particle itself, turning your spacecraft's own shielding into a source of danger. This phenomenon is a primary reason why human travel beyond the Moon to Mars or elsewhere is such a profound challenge. On a multi-year journey, the cumulative dose from these relentless particles would be unavoidable and severe. They pass through the body like microscopic needles, damaging cells and shredding DNA in a way that significantly elevates the lifetime risk of cancer, central nervous system damage, and cataracts. They are the ultimate background threat, the silent cost of every ticket to the stars. So how do we protect ourselves from a rain we cannot block? Traditional materials like lead or thick metals are almost useless as they generate even more secondary radiation. The search is on for smarter shields. Scientists are investigating hydrogen-rich materials like polyethylene plastic, the same stuff in grocery bags, because hydrogen nuclei are simple protons that can effectively slow down and absorb incoming particles without creating as much dangerous fallout. Some concepts propose storing the spacecraft's water supply or even the crew's waste in tanks surrounding the living quarters, using these essential resources as a protective barrier. Other, more futuristic ideas involve creating artificial magnetic fields around the ship, deflecting the charged particles away like an invisible umbrella. Each solution is a trade-off between weight, practicality, and effectiveness. Galactic cosmic rays represent a fundamental wall on the road to the planets, a reminder that the empty space between worlds is not empty at all, but filled with a faint, deadly drizzle from the graves of dead stars. This invisible assault on our cells has a devastating accomplice within our own bodies. Beyond the weakening of bones and muscles, microgravity orchestrates a silent, systemic collapse that strikes at the very core of our vitality. The hematopoietic system, the intricate factory inside your bones that manufactures your blood, begins to falter. In the absence of gravity's gentle stress, your bone marrow receives confusing signals. Its production of both red and white blood cells can become dysregulated. Some studies show a drop in red blood cell count, leading to a form of space anemia where the body struggles to deliver oxygen efficiently. But the more insidious effect is on the immune system. The white blood cells that serve as your body's standing army become confused and lethargic. Their ability to recognize pathogens, to mobilize, and to destroy invaders is measurably weakened. It is as if the entire defense force has been put on a sedative. This means an astronaut living in a sealed can with recycled air is paradoxically more vulnerable to everyday infections. A common cold virus brought up from Earth could spread more easily and hit the crew harder. Even more alarming is the reactivation of latent viruses the body usually keeps in check. Studies of astronauts before and after long-duration missions show that viruses like Epstein-Barr, which causes mononucleosis, or varicella zoster, which causes chickenpox and shingles, frequently reawaken. The suppressed immune system can no longer keep these dormant passengers locked down. This creates a double jeopardy. Radiation is shredding DNA and increasing cancer risk from the outside, while a hobbled immune system is less capable of hunting down and destroying aberrant precancerous cells from within. It is a perfect biological storm. The body's internal surveillance system is blinded just as the external threat level skyrockets. The implications for a multi-year mission to Mars are profound. A simple dental abscess or a minor wound infection could become a life-threatening crisis without a strong immune response. The dream of planting a flag on another world could be undone by a virus that has been sleeping inside an astronaut since childhood. Countermeasures are as crucial as they are challenging. Research is exploring pharmacological aids, specialized nutrients, and even artificial gravity through slow-spinning spacecraft sections to trick the body into maintaining its earthly defenses. Protecting the human body in space is not just about building stronger bones. It is about preserving the invisible cellular army that has kept us alive for millennia. That army, it seems, is unwilling to leave its home planet without a fight. Every breath and every sip on a long space mission is a testament to a delicate life or death alchemy. A spacecraft is a closed ecological bubble, a tiny island of biology adrift in an infinite sterile desert. The challenge of waste and contamination is not merely a matter of logistics. It is the fundamental struggle to keep your own biological processes from poisoning your fragile environment. The systems that keep astronauts alive must perform a miracle of near-perfect recycling. Every drop of water, from drinking to sweat to urine, must be reclaimed. Every exhaled breath must be scrubbed of carbon dioxide and replenished with fresh oxygen. The International Space Station's environmental control and life support system is a mechanical marvel, a complex web of filters, centrifuges, and chemical reactors. Yet perfection is impossible. Trace contaminants inevitably build up in the air and water, silent byproducts of human existence. Volatile organic compounds, or VOCs, off-gas from plastics, electronics, and even the crew themselves. Ammonia can leach from wastewater systems. In the confined volume of a spacecraft with no open window to clear the air, these compounds do not simply dissipate. They concentrate. Left unchecked, they can cause headaches, nausea, and long-term health issues. The psychological weight of this is immense. You are drinking water that was, quite literally, your own sweat and urine yesterday, purified through an intricate process. You are breathing air that has passed through the lungs of your crewmates countless times. The line between life support and life recycling becomes unnervingly thin. Then there is the more visceral challenge, human waste in microgravity. It is a problem of basic physics. Without gravity to pull things down, everything floats. The toilets on the ISS are engineering wonders of suction and airflow, designed to capture waste without letting it escape into the cabin. A malfunction or a missed seal is not just a messy inconvenience, it is a biohazard event, releasing bacteria and foul odors into the shared living space. The simple, private act of using the bathroom becomes a complex, sometimes stressful procedure. This constant intimacy with biological processes, the smell, the sound, the lack of any true privacy, grates on the human psyche over months. But the waste itself is only part of the story. The warm, moist environment inside a spacecraft is a paradise for microorganisms. Molds and bacteria find a welcoming home in air conditioning ducts behind panels and in the damp corners of hygiene stations. These microbes are not just a threat to health, they are a threat to the ship itself. They can form resilient biofilms that clog filters, corrode metal, and degrade seals and electrical wiring. There are documented cases of fungal growth damaging equipment on the Russian space station Mir. On a mission to Mars, a persistent mold infestation could sabotage critical life support machinery with no possibility of replacement. The battle against contamination is constant and fought on every front. Astronauts spend hours each week on cleaning, wiping down surfaces with disinfectant wipes, and maintaining the labyrinth of life support hardware. Air and water are continuously monitored by sensors and sampled for laboratory analysis. It is a silent, endless war against the natural tendency of a closed system to degrade into chaos. Your survival depends on winning this war every single day, on ensuring that the machine that turns your waste back into life does not become the very thing that ends it. Out in the void, there are no road signs, no maps, and no horizon to guide you. Navigation in space is a constant, high-stakes calculation against an infinite black backdrop, where a single error can send you spiraling into oblivion or on a one-way trip into the endless dark. On Earth, we take our cues from the world around us, the curve of a highway, the peak of a mountain, the steady pull of magnetic north. In space, these references vanish. There is no up or down, no left or right in the traditional sense. A spacecraft must create its own sense of direction and position from scratch, a process as delicate as it is vital. This is the domain of star trackers, inertial measurement units, and the distant voice of mission control. A star tracker is essentially a smart camera that takes pictures of the star field. It compares the patterns of stars it sees to a built-in celestial map, a cosmic fingerprint database. By identifying specific constellations, it can determine the spacecraft's orientation with incredible precision, like a sailor using the North Star, but with a computer's flawless memory. Meanwhile, an inertial measurement unit, or IMU, acts as the ship's internal sense of balance. Using ultra-sensitive gyroscopes and accelerometers, it measures every tiny rotation and change in velocity. It knows if the ship has begun to drift or turn, even by a fraction of a degree. These two systems work in a continuous dance, the star tracker providing absolute fixes from the stars, and the IMU tracking all the movements in between those fixes. The data flows into the flight computers, which constantly fire tiny thrusters called reaction control system jets to maintain perfect attitude, the spacecraft's orientation in space. This is not just for pointing antennas at Earth, it is for survival. Lose attitude control, and you lose the ability to generate power from your solar panels to communicate, to control your temperature, or to fire your main engine in the correct direction. The spacecraft begins to tumble, a helpless, spinning derelict. The threat is in the fragility of these systems. A star tracker can be blinded by the sun or a bright planet drifting into its field of view. A micrometeoroid strike could damage a critical gyroscope. A software glitch or a radiation-induced bit flip in the computer could send corrupted data to the thrusters, commanding them to fire in a way that puts the vehicle into a dangerous spin. History provides a stark lesson in manual navigation under duress. During the Apollo 13 crisis, after an explosion crippled the command module, the crew was forced to shut down all their guidance computers to conserve power for the desperate return home. To perform the critical engine burn that would swing them around the moon and back to Earth, they had to align their crippled spacecraft using only one tool, the sun. With the Earth and stars obscured by a haze of oxygen venting from their dying service module, Commander Jim Lovell manually rotated the ship until the sun appeared in a specific crosshair on his window, an ancient mariner's technique using the only reliable landmark left in their sky. It was a breathtaking moment of human skill overriding machine failure, a reminder that when the computers go dark, the only map is in the mind of the astronaut. For a probe heading to the outer planets, a similar error could be fatal. A trajectory correction maneuver fired just a few degrees off could mean missing a planetary flyby by hundreds of thousands of miles with no fuel left for a second chance. The spacecraft would sail silently past its target, becoming a permanent ghost in the interstellar wind. Every mission is a tightrope walk between absolute precision and catastrophic disorientation, a dance with the stars where one misstep means the music stops forever. That delicate dance of navigation can be shattered in an instant by a danger that, on Earth, we think we understand completely. Fire in microgravity is not the familiar, leaping flame we know. It is a silent, spherical predator that defies every instinct we have about how fire behaves. In a spacecraft, a fire is not just an emergency, it is an existential crisis. The reason lies in the absence of gravity. Here on the ground, hot air rises because it is less dense than the cooler air around it. This convection creates the familiar upward-pointing flame and carries smoke towards ceiling detectors. In space, with no up or down, convection vanishes. A flame does not rise. Instead, it forms an eerie, blue-hued sphere around its fuel source, a smoldering ball of chemical reaction that consumes oxygen in all directions at once. It burns at a lower temperature and can linger almost lazily as a persistent, incomplete combustion. This is a nightmare for detection. Since smoke does not rise, traditional ceiling-mounted smoke detectors are useless. Smoke simply expands in all directions, filling the cabin with a toxic haze long before an alarm might sound. And in a sealed environment, that smoke is a cocktail of poisons. It contains carbon monoxide, which binds to your blood and starves your tissues of oxygen, and fine particulate matter that can clog lungs and damage sensitive equipment. The limited escape options turn a small fire into a potential death sentence. On Earth, you run outside. In space, there is no outside, only the lethal vacuum. Your options are to fight the fire immediately, right where you are, or to retreat to another module and seal a hatch, hoping the fire will consume all the oxygen in the isolated section and burn itself out before breaching the barrier. The stark reality of this threat was demonstrated aboard the Russian space station Mir in 1997. A backup oxygen-generating candle, a solid fuel chemical device, malfunctioned and ignited. It did not explode, but it produced a raging, blowtorch-like jet of flame over 3 feet long, spewing molten metal and filling the module with thick, choking smoke. The crew, their eyes burning and lungs searing, fought the fire with multiple extinguishers. Communications with the ground were partially lost, and for terrifying minutes, they faced the very real possibility of having to abandon the entire station. They contained it, but the event left the station's interior coated in soot and the crew shaken, a permanent lesson etched in smoke. Today, the International Space Station is armed with a sophisticated, multi-layered defense. Specialized smoke detectors are placed in ventilation ducts where the station's forced airflow will carry any particles. Fire extinguishers use a fine mist or foam rather than powder, which would float everywhere and contaminate the entire environment. Perhaps most crucially, relentless research aboard the ISS studies flame behavior itself. Scientists ignite controlled, small fires in special chambers to observe how materials burn, how flames spread, and how to best suppress them in this alien environment. They have discovered that some materials that self-extinguish on Earth will continue to burn slowly in microgravity, a hidden danger in common objects. Every piece of material brought aboard is rigorously tested for flammability. Fire remains one of the top crew safety concerns, a shape-shifting enemy that forces us to relearn a primal element in a world without gravity, where a single spark can become a hovering, all-consuming sphere of doom. That profound shift in perspective is not always a source of inspiration. Gazing down at the swirling blues and whites of our planet from orbit can trigger a deep and destabilizing psychological crisis, revealing the dark side of the awe-inspiring overview effect. Astronauts often describe a sudden, overwhelming cognitive shift, the realization that every human conflict, every border, and every personal worry exists on that single, fragile sphere hanging in an infinite blackness. For some, this is a beautiful, unifying epiphany. For others, it becomes a source of profound anxiety and existential dread. The emotional whiplash can be severe. You are hit with the staggering beauty of Earth, followed immediately by the crushing understanding of its isolation and vulnerability. This can evoke intense feelings of insignificance, a sense that all human endeavor is meaningless against the cosmic scale. The very thing that makes you feel connected to all humanity can, in the same moment, make you feel utterly alone in the universe. This state is far more complex than simple homesickness. It can manifest as a form of dissociation, where the astronaut feels detached from their own life and identity, as if observing their existence from a great distance. The mission, with its detailed checklists and technical procedures, can suddenly feel trivial, creating a dangerous rift between the crew members' emotional reality and the operational focus required for survival. This duality is captured powerfully in astronaut accounts. Many speak of the life-changing beauty, but others hint at the struggle. Some have reported a form of cosmic sadness, a grief for the planet's fragility, and for the pettiness of the conflicts they can literally see from above. The late astronaut Piers Sellers described a complex mix of feelings, noting that while the view was magnificent, It also underscored how thin and tenuous our atmosphere is, a tiny little onion skin around the planet. The psychologist and researcher Dr. Nick Connors, who studied astronaut psychology extensively, termed this the Earth out of view phenomenon, noting that some crew members experienced a low-level depression once Earth was no longer visible, as if their primary psychological tether had been severed. This suggests the overview effect is not a single positive event, but a continuous emotional negotiation. An astronaut must balance this overwhelming cosmic perspective with the immediate, minute-to-minute demands of living and working in a hazardous environment. Too much absorption in the view could lead to a dangerous neglect of duties, while suppressing the emotion entirely could contribute to the grinding stress of confinement and isolation. Training now seeks to prepare astronauts for this emotional tsunami, not just the physical rigors. They undergo psychological screening and resilience training, and debriefings after missions provide a space to process these complex feelings. The goal is not to prevent the overview effect, but to help spacefarers integrate its profound and sometimes terrifying message without losing their connection to the mission or to themselves. The most stunning view in human experience, it turns out, can also be a mirror reflecting our deepest fears of loneliness and impermanence back at us. That cosmic perspective forces us to ask a deeply unsettling question about our own biological baggage. Every spacecraft we launch is not just a machine, it is a potential ark carrying a hidden cargo of microscopic Earth life. This introduces the twin specters of contamination, a danger that could sabotage our greatest scientific quest and, in our darkest fears, threaten our very world. First, there is forward contamination. This is the risk that our robots and eventually our astronauts will carry hardy Earth microbes to other planets. Imagine a bacterium from Florida clinging to the leg of a Mars lander, surviving the journey, and then being deposited in a moist, salty patch under the Martian surface. If we later discover what looks like life there, how could we ever be sure it was not just our own hitchhiker? This is not a trivial concern. We know that certain extremophile bacteria can survive the vacuum of space, intense radiation, and freezing temperatures. They could lie dormant for years to protect the pristine environments of other worlds and preserve our ability to answer the ultimate question: are we alone? We enforce strict planetary protection protocols. Spacecraft bound for places like Mars or the icy moons of Jupiter are assembled in pristine cleanrooms where engineers dress head to toe in bunny suits and the air is constantly filtered. Components are baked at high temperatures, bathed in harsh chemicals, or zapped with radiation to sterilize them. The Mars rovers, like Curiosity and Perseverance, were subject to these rigorous procedures, their metal bones scrubbed cleaner than any surgical instrument. The goal is to reduce the microbial load to an almost unimaginable level, ensuring we are sending a scientist, not a contaminant. But the fear also flows in the other direction, known as back contamination. This is the science fiction nightmare, the plot of the Andromeda Strain. What if, in our search, we inadvertently bring back an extraterrestrial microorganism, a pathogen for which Earth life has no defense? The scientific consensus is that the probability is extremely low. Any native Martian life, if it exists, would have evolved along a completely separate biochemical pathway for billions of years. It likely would not recognize our cellular machinery as food, just as a tree fungus does not give humans a cold. However, the consequences of being wrong are so catastrophic that we treat the risk with utmost seriousness. This is why samples returned from Mars will be handled with more caution than the deadliest plague. The current plan involves a multi-stage containment system. The sample return capsule would land and be retrieved in a sterile manner, then transferred to a receiving facility that is essentially a biological maximum security prison. The rocks and soil would be studied inside sealed, redundant containers by scientists using robotic arms. analyzed for any sign of biohazard before they are ever exposed to Earth's biosphere. These protocols are not born of paranoia, but of profound responsibility. They represent a promise to the universe and to ourselves that our curiosity will not become carelessness. In seeking new life, we must guard the one we already have, ensuring our first contact is one of discovery, not disaster. Physics itself becomes a prison, a set of unbreakable chains that bind every dream of exploration. The most formidable danger in space is not a hostile force, but a simple, brutal equation. The tyranny of the rocket equation defines the very limits of our reach. At its heart is a devastatingly simple truth. To accelerate a spacecraft, you must expel propellant out the back. But to carry that propellant, you need more fuel to lift its weight. And to lift that extra fuel, you need even more. It is a vicious, exponential cycle where every kilogram of payload you wish to deliver to another planet requires many, many kilograms of fuel at launch. This creates a razor-thin margin for everything. There is no room for generous safety buffers, no capacity to pack extra fuel for unforeseen emergencies or major course corrections. Your mission is a high-wire act with almost no net. This physics trap dictates the architecture of every mission. It is why spacecraft are stripped to the bone, why every bolt and wire is scrutinized for weight. It forces engineers into agonizing trade-offs. Do you add more radiation shielding for the crew, or do you carry more food? Do you include a backup life support system, or do you shed that weight to ensure you can even reach your destination? The rocket equation is the reason why a mission to Mars is not a journey of constant propulsion, like a car driving across a country. Instead, it is a series of precisely calculated one-time pushes. You fire your engines to escape Earth, then you coast for months along a celestial highway called a Hohmann transfer orbit, a fuel-efficient ellipse that uses the sun's gravity to swing you from one planet's orbit to another. This path is not a matter of choice, it is a mandate from physics. It creates the concept of launch windows. Because both Earth and Mars are constantly moving, you can only launch when the planets are aligned in just the right way, so that when you complete your coasting arc, Mars arrives at the exact same point at the exact same time. This window opens for only a few weeks, approximately every 26 months. Miss it and you wait for over 2 years, but the precision demanded is terrifying. A small error in your initial engine burn, a slight miscalculation, means you will not arrive at a rendezvous with Mars. You will arrive at the point in space where Mars was, or where it will be, but not where it is. The result is a lonely flyby, a permanent exile into solar orbit with no hope of rescue, because you simply do not have the fuel to correct a major mistake. There are no gas stations between the planets. This unforgiving math also strangles abort options. On the Apollo missions to the Moon, if something went wrong, the crew could theoretically use the lunar module's engine or the command module's engine to perform a direct abort to turn around and come home. For a spacecraft coasting to Mars halfway through its journey, turning around is a physical impossibility. The energy required to cancel your orbital velocity and head back to Earth would demand a fuel supply many times larger than what launched you in the first place. You are on a one-way street with no U-turns. Every decision, every gram is locked in place by this equation. A reminder that before we can conquer the stars, we must first submit to the cold, hard logic of a numbers on a page. Our ambition is boundless, but our baggage allowance for the trip is brutally, infinitesimally small. This relentless physics of scarcity forces every component aboard a spacecraft to be perfect, but perfection is a human ideal, not a guarantee of metal and silicon. In the unforgiving theater of space, a single bolt, a solitary valve, or one microscopic crack in a seal holds the power to write a mission's final chapter. This is the danger of single-point failures, where the entire complex symphony of a mission hinges on one tiny, fragile note. The philosophy of engineering for space is therefore not about building things that never break. That is impossible. It is about building systems where nothing is allowed to break alone. This is the doctrine of redundancy. For every critical function, there must be a backup, and often a backup for the backup. A spacecraft might carry 2, 3, or even 4 independent flight computers, so if one is zapped by radiation, another instantly takes over without a flicker. Fuel lines have redundant valves, life support systems have parallel pumps and scrubbers, electrical power flows through multiple isolated channels. It is a mechanical version of not putting all your eggs in one basket, because in space, dropping that basket means everyone dies. Yet redundancy itself is a heavy, complex compromise. Every backup system adds weight, cost, and its own new points of potential failure. The engineer's nightmare is a common mode failure, a single flaw that defeats all the redundancies at once. The classic harrowing example is Apollo 13. The mission was crippled not by the failure of a primary system, but by the explosion of a single oxygen tank. A tiny thermostat switch designed to heat the tank's contents had been inadvertently left on during a ground test years before. The switch fused shut, and during a routine tank stir in flight, it caused a wire to overheat, igniting the Teflon insulation. The tank exploded, blowing off the side of the service module and venting the crew's oxygen and power into space. The redundancy existed. There were 2 oxygen tanks, but the explosion damaged the second one as well. The backup became a casualty of the primary's failure. The crew's survival then depended on a breathtaking series of improvised solutions, using the lunar module as a lifeboat, a scenario never fully planned for. Decades later, in 2022, a different kind of single-point failure threatened the International Space Station. A Soyuz crew capsule docked to the station began spraying coolant into space from a microscopic puncture, likely caused by a micrometeoroid strike. This was not an explosion, but a slow, silent bleed. The coolant was essential for regulating the capsule's temperature during the fiery re-entry through Earth's atmosphere. Without it, the interior would become an oven, killing the crew on their way home. The spacecraft itself, the very vehicle designated as the crew's lifeboat in an emergency, was now a death trap. The failure was in a single, unshielded coolant line. There was no backup for this. The solution was unprecedented, launching an empty replacement Soyuz capsule for the crew to use as their ride home, while the damaged vehicle was sent back unmanned. These events reveal a humbling truth. We can test components in vacuum chambers, on shaker tables, and in radiation ovens, but we cannot perfectly simulate the combined, years-long assault of the actual space environment. A material behaves differently after years of thermal cycling. A seal degrades under constant ultraviolet bombardment. A computer chip's lifespan shortens under the relentless drizzle of cosmic rays. Failure is a teacher, but its tuition in space is catastrophically expensive. The quest for reliability is a war against entropy, fought one bolt, one wire, and one line of code at a time, knowing that somewhere, hidden in the millions of parts, is the one we missed. Our minds are built for a world of constant sensory feedback, a symphony of cues we never even notice until they are gone. In the sterile, silent can of a spacecraft, that symphony is replaced by a monotonous hum. Sensory deprivation in space is a slow, insidious thief, robbing the brain of the very information it uses to construct reality. The first thing to vanish is the sense of gravity itself. Your inner ear, the vestibular system, is a beautiful gyroscope filled with fluid and tiny hairs. On Earth, gravity pulls that fluid down, telling your brain which way is up. In microgravity, the fluid floats freely, sending chaotic, meaningless signals. The result is spatial disorientation so profound it can trigger immediate and violent nausea, the dreaded space adaptation syndrome that affects roughly half of all astronauts. But the disorientation runs deeper than the stomach. Without a reliable up or down, the brain struggles to map its surroundings. an astronaut can suddenly feel like the ceiling is the floor or that they are perpetually falling even when perfectly still. This can lead to dangerous illusions. During a spacewalk, an astronaut might perceive their own stationary spacecraft as drifting away from them, or misjudge the distance to a critical handhold, a mistake that could mean floating off into the void. The lack of varied sensory input does more than confuse. It can actually manufacture sensations. In the constant, droning white noise of life support, with no breeze, no distant sounds, and a limited palette of smells, the starved brain sometimes starts generating its own stimuli. Astronauts have reported auditory hallucinations, hearing phantom alarms or even music. Some have experienced vivid flashes of light or color, not from cosmic rays, but from a mind trying desperately to fill the sensory void. This cognitive strain contributes to a phenomenon veteran spacefarers call the space stupids. It is not a loss of intelligence, but a noticeable slowdown in mental processing. Simple, routine tasks take longer, decisions become hesitant. An astronaut might reach for a tool and fumble it, or misread a familiar checklist, not from carelessness, but because their brain is expending enormous energy just to maintain a basic sense of orientation in a world without the rules it evolved with. The countermeasures are a testament to our understanding of this neurological need. Spacecraft and stations now meticulously simulate Earth-like cues. Lighting systems are programmed to follow a 24-hour day-night cycle, using blue-white light to simulate morning and warmer tones for evening, helping regulate circadian rhythms that would otherwise drift into chaos. Mission planners intentionally introduce variety, scheduling video calls with family, uplinking the sounds of rainforests or bustling cities, and even sending up care packages with distinct, comforting smells like fresh grass or baked goods. These are not luxuries, they are psychological life support, tiny anchors to a sensory world that keeps the human mind from unraveling in the silent deep. This silent, internal pressure reshapes the very windows to the soul. Spaceflight-associated neuro-ocular syndrome is not a temporary inconvenience. It is a lasting, physical alteration of the human eye, a danger written in the delicate tissues of the retina and optic nerve. The current understanding paints a clear yet alarming picture. In microgravity, the fluid that normally pools in your legs and lower body redistributes upward toward your head and chest. This extra volume increases the pressure inside your skull, a condition doctors call intracranial pressure. That pressure has nowhere to escape, so it seeks the path of least resistance, pressing against the back of the eyeball. The optic nerve, the vital cable that carries visual information to the brain, becomes swollen. The eyeball itself, under this persistent force, can actually change shape, flattening at the back. Think of gently pressing your thumb against a ripe grape. The structure gives way. For an astronaut, this translates to a slow, insidious degradation of sight. They might experience blurred vision, a need for reading glasses where none were needed before, or a noticeable change in their distance prescription. The data is sobering. Over half of all astronauts who spend extended time on the International Space Station return with some measurable degree of these ocular changes. For many, the condition partially reverses upon return to Earth, as gravity pulls the fluids back down and the pressure eases, but for a significant percentage, the damage is permanent. Their eyes are literally, physically different than when they launched. Follow-up examinations, sometimes years later, show persistent flattening of the eyeball and folds in the light-sensitive retina, a permanent scar from their voyage. This transforms a mission to Mars from a question of engineering into a profound medical dilemma. A 6-month journey, a year and a half on the surface, and a 6-month return home means years of sustained intracranial pressure. Could an astronaut's vision degrade to the point they could no longer perform critical tasks, like piloting a landing or reading complex instrument panels? Could they be left with permanently impaired sight as the price for walking on another world? the race to find a countermeasure is urgent and ingenious. One of the most promising devices looks like a vacuum cleaner for the human body. It is a lower body negative pressure chamber, essentially a sealed cylinder that fits around an astronaut's waist. By creating a gentle suction, it artificially pulls bodily fluids back toward the legs, mimicking the effects of gravity. Early tests on the space station suggest regular sessions in this device can reduce the pressure in the head and may help protect the eyes. Other research focuses on specialized goggles that apply a slight vacuum to the eyes themselves, or on medications that could reduce fluid production or protect the optic nerve. Every MRI scan of an astronaut's eyes, comparing the before and after images, is a stark map of this hidden frontier. It reveals that the final frontier may not just challenge our machines and our muscles, but permanently rewrite the very way we see the universe. Even permanent changes to your vision cannot shield you from the slow, grinding weight of sameness. The 23rd hidden danger is not a violent force, but a creeping void, the psychological erosion of boredom and routine inside a metal can hurtling through nothingness. On a mission to Mars, the vast majority of the journey, perhaps 9 months each way, will be a featureless cruise. The initial adrenaline of launch fades, Earth shrinks to a dot and vanishes, and you are left with the same small space, the same faces, and the same daily checklist. This is not the dramatic isolation of a crisis, but the chronic, soul-deadening monotony that can quietly sabotage a mission from within. Vigilance drops. A crew member performing a routine systems check for the 100th time might glance over a reading, their mind elsewhere. A procedural step committed to muscle memory might be skipped. In an environment where a single missed warning light or a forgotten valve sequence can cascade into catastrophe, this lapse in attention is a genuine operational hazard. The human brain, wired for novelty and stimulus, begins to starve. Motivation to maintain rigorous physical exercise, the very thing keeping bones and muscles from wasting away, can wane when every day feels identical. Crew cohesion, so carefully selected, can fray under the petty irritations magnified by endless proximity, with no new scenery or external events to reset the social dynamic. We have glimpsed this mental grind in the diaries of polar explorers, men like Ernest Shackleton's crew trapped in the Antarctic ice. They wrote of the polar ennui, a debilitating lassity that set in during the endless winter darkness, where the sheer monotony of survival became a burden as heavy as the cold itself. In space, the schedule itself becomes a double-edged sword. Structure is essential for sanity and efficiency, but when every hour is planned, the future can feel like an endless loop. Astronauts on the International Space Station combat this with deliberate countermeasures. Their mission planners intentionally weave variety into the fabric of their weeks. Yes, there are hours of maintenance and science experiments, but there is also time allocated for personal hobbies, whether it is playing a guitar, practicing photography of Earth, or growing chili peppers. The arrival of a cargo ship is a major event, breaking the routine with new supplies, fresh food, and letters from home. Perhaps one of the most powerful tools is virtual reality. An astronaut can strap on a headset and for 20 minutes they are not in a module 250 miles up. They are walking through a forest, hearing birdsong and rustling leaves, or standing on a beach feeling the visual pull of a sunset. It is a sensory reset button for a starved brain. Meaningful work is another anchor. The knowledge that your experiment could help future explorers or unlock a secret of human biology provides a purpose that transcends the daily grind. The danger of boredom reminds us that keeping a crew alive is not just about oxygen and water. It is about feeding the human spirit. For a trip to Mars, we must engineer not just a ship, but an entire way of life, a miniature society with its own rhythms, surprises, and sense of purpose, or the vast emptiness outside will find its way in through the cracks of a weary mind. The final frontier holds a deeper darkness, a realm beyond the edge of our sun's protective influence. For all the dangers we can name and attempt to engineer against, the 24th and perhaps most profound hazard is the simple, terrifying weight of the unknown. We have never sent a human being beyond the moon. Every plan for Mars and beyond is built on extrapolation, on data from unmanned probes and theories tested in labs. But the true environment of deep space, beyond the heliosphere where the sun's magnetic bubble gives way to the interstellar medium, is a mystery. The twin Voyager probes are our only scouts in that vastness, and their whispers back to Earth hint at a stranger place than we imagined. Out there, the composition and intensity of cosmic radiation could shift in ways our shielding isn't prepared for. The density and behavior of the sparse interstellar gas and dust through which a ship would plow at tens of thousands of miles per hour could pose unforeseen abrasion or electrical charging risks we haven't modeled. And then there is the profound psychological milestone of crossing that threshold, where the sun ceases to be a bright, defining disk of light and becomes merely the brightest star in a sea of stars. The comforting, familiar anchor of our solar system would truly vanish. The overview effect would be replaced by something else entirely, a sense of being utterly untethered, adrift between stars with no visual proof of home. This loss could trigger a form of cosmic agoraphobia, a paralyzing awareness of scale for which no earth-bound experience can prepare the human mind. But the greatest unknown is the one we cannot even conceive. Are there regions of space with subtle gravitational anomalies or pockets of unexpected particle density? Could there be phenomena related to dark matter or cosmic rays that only manifest over journeys lasting decades? Our probes have not encountered show-stopping horrors, but they are simple, robust machines. A human body, with its exquisite biological complexity, is a far more sensitive instrument. The ultimate danger of a generations-long voyage is that the ship and its crew might slowly unravel from a cause we never saw coming, a silent, invisible stressor that only reveals itself when it is far too late to turn back. For all our meticulous lists and risk assessments, the universe has a way of surprising us. The final, humbling truth is that our greatest peril in the deep dark may not be any of the 23 dangers we have named, but the 24th, the one waiting in the silence we have not yet learned to hear. All our planning for the unknown cannot shield us from a danger born right here at home. The final and perhaps most frustrating threat to our future in space has nothing to do with radiation or rocket science. It is the shifting, unpredictable landscape of economics and politics on Earth. A mission that survives the vacuum can be killed by a budget cut. A program that endures years of engineering can be cancelled with the stroke of a pen. The grandest visions for exploration are tethered to the volatile will of nations and the balance sheets of governments. This ground-based peril is a constant, quiet tremor beneath every launch. Consider the gap that followed the retirement of NASA's space shuttle. For 9 years, the United States, the nation that put humans on the moon, had no way to launch its own astronauts into orbit. American crews could only reach the International Space Station by buying seats on Russian Soyuz rockets, a situation that left the entire program vulnerable to geopolitical tensions. If relations had soured, that vital taxi service could have vanished, potentially stranding astronauts on the station without a guaranteed ride home. It was a stark lesson in how earthly disputes can sever our lifeline to the stars. Every mission exists on a financial knife edge. A new administration with different priorities can redirect funds, scrapping decades of work. A single failed launch or a high-profile accident can erode public and political support, turning the dream of Mars into a line item deemed too expensive or too risky. The monumental effort to build a spacecraft is meaningless if the political will to fund its launch evaporates before it ever leaves the ground. This vulnerability extends beyond funding into the realm of security. Space is no longer a sanctuary, it is a contested domain. Nations have tested anti-satellite weapons, deliberately blowing up their own old satellites in demonstrations of force. Each test creates thousands of new pieces of debris, adding to the lethal cloud in low Earth orbit and directly threatening every other satellite and crewed vehicle in that region. It is an act of terrestrial conflict that pollutes the shared commons of space for everyone for generations. The destruction of a single critical satellite, whether by accident or aggression, could cripple global communications, blind weather forecasting, and disrupt the financial networks that underpin modern life. The danger is no longer just natural, it is deliberately manufactured. This political and economic fragility underscores a profound and often overlooked truth. Reaching space is a triumph of engineering and courage, but staying there, building a sustained human presence beyond Earth, requires something far less predictable, stable, and enduring support from the planet we left behind. Our greatest voyages are conceived in imagination, built with technology, but ultimately launched on a foundation of earthly peace, cooperation, and commitment. Without that foundation, the ship may never leave the dock, or it may sail into a sky we have deliberately filled with arrows. The journey we have just taken reveals a cosmos of staggering hostility. From the invisible bullets of cosmic radiation to the clinging, toxic dust of alien worlds, from the mind-bending disorientation of microgravity to the silent, creeping dread of deep space isolation, we have mapped a landscape of 25 profound dangers. We have confronted the vacuum's lethal embrace, the sun's explosive fury, and the high-speed minefield of our own orbital debris. We have seen how fire becomes a spherical predator, how our own immune systems turn against us, and how the simple physics of a rocket equation can become an inescapable prison. The threats are both cosmic and profoundly human, woven from the fabric of the universe and the fragile nature of our own biology and politics. Yet here is the paradox that defines our species. Space exploration is humanity's greatest adventure, not in spite of these perils, but precisely because of them. The monumental challenge is what makes the endeavor worthy. It forces the very best of our ingenuity, courage, and cooperation to the surface. Every day, an army of brilliant engineers, meticulous scientists, and steadfast astronauts stands on this front line. They design the Whipple shields, they model the radiation doses, they train for psychological resilience, and they painstakingly sterilize every bolt bound for Mars. They are the quiet heroes who transform a list of terrifying impossibilities into a checklist of managed risks. Our future among the stars depends on this relentless collective effort. So, what can you do from right here on Earth? Stay curious, stay supportive. The first, most crucial step in conquering any frontier is to understand its dangers with clear-eyed honesty. By learning about these hidden threats, you become part of the mission. Your interest fuels the public will that drives exploration forward. Share your wonder. Which of these dangers surprised you the most? Are there other cosmic mysteries you are burning to understand? Let that curiosity be your compass. The universe is vast and its secrets are endless. If you want to keep exploring them with us, make sure you are subscribed for more deep dives into the cosmos. The adventure is just beginning, and every new discovery starts with a question asked from a fragile, beautiful planet looking up at the starry dark.